Hi there, so today in this video we're going to cover what happens biochemically in your body whenever you take a breath in and then you eventually release it. So the first step is taking a breath in and having O2 or oxygen from the environment come into your lungs and then into the alveoli of the lungs. And if we can look here at this zoomed in image of an alveoli, they are butted right up next to our circulatory system, so our arteries and our veins. And what can happen here is that we have gas diffusion down a gradient. So we have a very high concentration of oxygen inside the lungs alveoli because we just took that big breath in. But we have a very low concentration of oxygen inside our circulatory system because at this point the blood is deoxygenated. So we have the oxygen go down its gradient from the alveoli into our circulatory system. And the same can be said for the concentration of carbon dioxide, except for it travels in the opposite direction, but we'll cover more of that towards the end of the video. So the first thing, once oxygen comes into our body, is we can look at the Peretz equation that relates deoxy and oxygenated hemoglobin. And so what we can see is originally this hemoglobin coming from the veins is deoxy, or T state, meaning it is not bound by oxygen, but rather bound by a proton. And so what happens is since the partial pressure of oxygen is so high at 100 torr in the lungs, and the P50 value of hemoglobin is 26 torr, what we have happen is the hemoglobin will bind oxygen because its P50 is much less than the pressure of oxygen in its environment. And so this, in turn, affects the Peretz equation. Instead of being a deoxy or T state hemoglobin, we transfer over to be an oxy or oxygenated R state hemoglobin. And so we can see the oxygen comes in, bounces here, bounces over here, and then this oxygen can go down our arteries towards our distal tissues. Okay, so since we have a partial pressure of oxygen in the distal tissues of 30 torr, and our hemoglobin has come down and it has a P50 value slightly less but almost equal to the partial pressure in the distal tissues, we're going to have some interesting things happen. So myoglobin, a different type of globin protein, is stationed here in our tissues, and its P50 value is 2.8, which is 10-fold less than that of hemoglobin. So, hemoglobin will dump off its oxygen molecules to the myoglobin, mainly for two reasons. The first being that since the hemoglobin's P50 value is nearly equal to that of PO2, it doesn't really have anything to really want to hold on to. And then also, the pressure of oxygen in the environment is much, much greater than that of the P50 value of myoglobin. So for those two reasons, myoglobin has a much stronger affinity for the oxygen molecule than hemoglobin does. It has a much greater affinity. And so what happens after this is we have this oxygen come down, like I said, down through the arteries and into our distal tissues to myoglobin, and myoglobin delivers this oxygen throughout the distal tissues. And then this oxygen can enter what is called the fuel equation, where fuel, some type of carbon source, plus the oxygen can yield carbon dioxide, H2O, and ATP, a form of energy. And so, like I said earlier, we're going to follow the path of CO2 a little bit later at the end, so we'll just kind of finish up what happens here with the oxygen molecules. So since we've generated this energy, we need to use it. We spent a lot of time making it. And so this ATP can then enter our exercise equation. And so what happens here is that ATP energy reacts with water to form ADP, inorganic phosphate, a proton, and energy. And so the value of this energy that is produced is 30.5 kilojoules per mole per ATP molecule. And another interesting thing that comes from this exercise equation, other than this energy to fuel our body, is these protons. And so what happens if we follow these all the way back up to the Peretz equation, we encounter something called metabolic acidosis, where we are lowering the pH of our blood. And the reason that this happens is because we are increasing our amount of H plus ions, which is the same thing as saying that we're decreasing our blood pH. And so since we're having a lot more of reactants on this side, we're going to shift the equilibrium to being deoxy or T state. And this is important because, and it makes a lot of sense, because if you're running and exercising, you're using up all of your oxygen. So you're going to want to favor where you're releasing that oxygen to myoglobin to be able to produce more energy for your body. It's also important to note here that in this Peretz equation, the binding of oxygen or the binding of protons are completely mutually exclusive. So either oxygen is bound, like in the oxy R state, or a proton is bound in the deoxy T state. Even though they bind in different locations, the hemoglobin can either only bind one or the other. So up until now, we've covered basically the entire path of oxygen, but we've not yet covered what happens to release carbon dioxide from our body, because we know that that is the product of whenever we breathe in and then eventually breathe out. So we can come back here and look at our fuel equation. Whenever we added oxygen to this, carbon dioxide was one of our products. And so what we can have happen here is that since carbon dioxide is basically cytotoxic and deadly to just have floating around our body, we need to convert that into something safer to transport around until we can make it up to our lungs. So what happens is our good friend carbonic anhydrase is what can convert this carbon dioxide eventually to bicarbonate. And whenever you're in the distal tissues, this reaction runs in the opposite direction that it'll eventually run when we're up here at the lungs. And so the importance here is that this equation is actually reversible. So what we see down here in the distal tissues is that carbon dioxide produced from our fuel equation reacts with water and is helped out by our good friend carbonic anhydrase to produce bicarbonate, which is a safe substance to be transported through our circulatory system. So we have bicarbonate enter our veins, and it can travel back up towards the lungs, but we encounter a problem again when we get to the lungs, because we know we don't exhale bicarbonate, we exhale carbon dioxide. So we have this equation down here in its reversed form up here, where we're reacting bicarbonate with a proton with the help of carbonic anhydrase to produce carbon dioxide and water, which we exhale. And so that is the basics of how the biochemical reactions happen inside our body when we take a breath.